Okay, we're going to do SN2 now. SN2 is a concerted mechanism, meaning you only have one step. This is the whole mechanism actually. And the factors that you need for SN2 are, you need your nucleophile, in this case our nucleophile is the OH. You need your substrate, in this case it's going to be this molecule right here. So I'm going to draw the two CH3s right here. I have two, 1, 2, and then I'm going to draw the CH. And then we need a good leaving group. So leaving group, and in this case we have Br. Halogens make excellent leaving groups. So every time we see a halogen, we know that SN2 is positive. So the mechanism is your nucleophile attacks the carbon that is bonded directly to the leaving group, and then the leaving group leaves with the electrons. And this is the result. So this overwent SN2, and that's what happened. Now, what we see here is a backside attack. It's attacking the carbon from the back. It cannot attack it from here because there is crowding. There is electron hindrance. This one, we gotta remember, has 1, 2, 3, 4, 5, 6 electrons outside. So there is definitely steric hindrance on that side. So it's going to do a backside attack where this H is. I can even draw the H for you right here. So there is not crowding here. There is no big bulky groups there. So that will allow the nucleophile to get in. And then what we get is what is called an umbrella effect, which if you think of it, this carbon to be this part of my hand and the groups attached to it are that way. As this nucleophile gets in, then all the groups are going to be to the other side. It's an umbrella effect. It's because this one, if you think of it, this is going up because of all the electron density in this one. Once you attack it from the back, all the groups are going to come to this side because of the electron density on this group, this one. So, okay, so an example of SN2. We have our substrate right here. We can identify the leaving group right here. And then we have our nucleophile here. So I picked this example because this is to get an elongation of the carbon chain. So it's going to be an SN2, and the expected product should be our substrate, and then our nucleophile. Okay, so now let's see the mechanism and how we arrived at that answer. I'm going to copy this part. I'm just copying it. CH2, CH2, Cl plus CH triple bond C minus. Okay, so we can identify the three like we did up here. We say we have our substrate, good leaving group, and nucleophile. So what's going to happen is, we said it's a concerted step. Well, this one attacks the carbon directly attached to the leaving group. Then the leaving group is going to leave and take the electrons with it. So our product is CH2, CH2, and then C triple bond CH. Now, we did get our product, and with this we can, let's say you want to get an alkane from this, you just gotta treat the product. This is aside from the mechanism. The mechanism ends there, but let's say you want the alkane. You can just treat it with plus H2 in the presence of PD and carbon. So if you add 2 moles of this, you will get an alkane. If you add just 1 mole of this, of H2, then you will get an alkene, a cis alkene. So I guess cis and trans doesn't really apply here because we have 2 of the same group attached to the same carbon. But if this chain was longer, then we could be able to do cis and trans. If you wanted a trans, then you would add Na and NH3. But your mechanism of SN2 ends here. Again, what happened is our nucleophile attack our substrate, the carbon right that is attached to the leaving group, and the leaving group left, it's a concerted step, 1 step, that's it. Okay, another example. We check again, we have our nucleophile, we have our leaving group, and we have the substrate. Now, yes, this one can be a leaving group, but this is not a base strong enough to displace this leaving group. So the carbon that has the target is the one that's attached to the Br. The nucleophile has to be a better base than the leaving group in order to displace it. That's why we're not even going to take in consideration this one. NH2 is a better base than OH minus. So the expected product in SN2 should be our substrate, CH2 and H2, and the base attached instead of the leaving group. Now let's see how that happened. But before we do that, I want to make a note that this is a chiral carbon, and you have 4 different groups attached to it. You have a CH3, a Br, an H, and this group right here. So if we look at the conformation of it, we're going to see that Br, we take it as group 1, this will be group 2, and this will be group 3. So it is going counterclockwise, so it's going to be S. So just keep that in mind. Now, I'm going to copy this. CH, Br, CH2, and NH2. Then plus OH minus. Now we said that the OH minus, the nucleophile, is going to attack this carbon that has the good leaving group. This is not a good leaving group. So we attack that. And in a concerted step, while that attacks that, the leaving group leaves with the electrons. So what we get is this. CH3, C, H, the OH up here, and then our other group, CH2 and H2. And now, we said that this was a backside attack, and then there's an inversion of configuration. Inversion of configuration is, if we check this, we're going to see that this is our group 1, this will be 2, and this will be 3. So it's coming this way. So this molecule, now it's R. So it started as an S, but SN2 gives inversion of configuration, meaning you're going to end up with an R product. And that's it.